Welcome back. So in this video we will talk about pumps running in series in a short pipeline. Now we will discuss the basic of operation and the control, how we design the control system for them and why some of them doesn't work and what is the option we have. Before we go any further in the video, there is a couple of other videos discussing also pumps and running in parallel or in series and driven by VFD or has a control valve. So please go to Lunch and Learn channel. In the playlist Dynamic Simulator, you will find 3 videos discussing VFD Driven Pump and how you simulate it in Excel, and also 2 pumps running in parallel with driven by VFDs, how you simulate them, and how you operate pumps with control valve and working again in parallel. So let's start. So the first thing we will look at is our system curve. System curve is the relationship between the flow rate and the work or the differential pressure or the head required to pass this flow rate from point A to point B, and point A being the discharge of your pump, point B is your next vessel or equipment. Of course, we have to consider as well the pressure at the vessel if we using this in our calculation. Of course, this is defined by the process engineer. They will define the minimum and the normal and the maximum operating condition. And on this curve, we will have those 2 or 3 points. When you buy the pump curve should be above your maximum. That means it can deliver more than the flow rate. At the maximum flow rate, it can deliver more than the differential pressure required or the head required. Now we have this curve of your pump and we have the curve from our process. So assume from our process we need a 400 meter head. Now for some economical reason or for some technical reason we cannot satisfy the flow rate with the required head by 1 pump. So we'll go with 2 pumps. So each pump will share half of the head. So this one will be 200 and this one will be 200. Of course, this is pump 1, and because they are identical, what we do is we multiply the head, because if this is 0, this pump adds 200 and this pump adds 200 on top of its suction pressure. So the discharge will be 400. So if you have any 2 pumps in series, what you do is you add the 2 curves together and that will give you the total curve of this pump. So far we put them and we call this as a close coupling scenario or a setup. Now assume for some reason we move this pump to the middle of the pipe. So here we said it's 5-kilometer pipe and we will move it to the middle. So what we expect is, if this is the middle, still we need 200 from this point to the suction of the second point, and then another 200 meter from the suction of the second pump to the end of the pipe. So everything is fine, everything is great, we have no issue whatsoever. Now, you can't assume that you will be able to put the second pump exactly in the middle of the line or in the middle of where is your differential pressure required or head required. Sometimes because of the power supply, sometimes because of the structure of the pipe and the ground and the construction. So it could be, let's say, 2 kilometer in one place and 3 kilometer in another, or 2 kilometer in the other. So how we control a close coupling setup? In a close coupling setup, we can assume that if the first pump running at 50%, we need the second one to be running at 50% as well. So the LIC, which controls the level in here and in this vessel, will run the 2 pumps at the same speed. But of course, if you run this pump for more time, then probably this pump is a little bit has wear and tear in it. So you need to increase or decrease the speed of the second pump or the first pump. So we just add a small bias, maybe 5% to the output of the LIC. So this one will be running at 70% speed. This one will be running at 70% plus 5%. Now this is the close coupling arrangement. So now we will move this guy again to the middle of the line. Now the temptation here is that we use the same scenario, and that's what we did before. We said run this at 50%, run that at 50%, and still we have our bias for each one of them. But the problem we have now is this is a 3 kilometer here and this is a 2 kilometer here. So that's mean the differential pressure required from this pump is not exactly the same as the required from the second pump. Exactly the same problem when we have 3 or more on the same pipeline. And furthermore, we have another problem. Some of the pipeline, they design it that if you have this pump fail, this pump will have some capacity and the power to be able to push the fluid from the suction pressure to the next pump. So it actually pushing it from here to the section of this and through the second pump to the third pump. Of course, the scenario of running both pumps or the 3 pumps or 2 pumps at the same speed, it doesn't look it will work. So, but we need to prove it by simulating the system. So in this Excel sheet, what it is, I have 2 pumps running and they are identical, and I have some process. The process curve change with the line, and as you can see here, I have a 2 kilometer line, 3 kilometer and 4 kilometer. So each one has its own process curve, and I have my pumps here. But to make it a little bit better this time, I decided to make a macro, and I have a user form here. We'll run it. So as you can see now, we are in the variable speed pumps. We have 2 pumps in a pipeline, and the length between the pump 1 and pump 2 and the discharge is defined by those push buttons here and those push button here. So we can define that this 3 kilometer or 2 or 4 and the other one exactly the same. Now we have to put here how many meter cube per hour we would like to go through, and the software will calculate the speed of this pump and the speed of this pump and the required head for each one. So as you can see now, for 200 meter cube per hour, we need 15 meter head for the first pump and 15 meter head for the second pump, because both of them are 2 kilometers. Now let's put a 3 kilometer distance between 1 and 2 and do the same calculation. So to run the first pump with 47, almost 47% speed, and the second one is 38.7 speed. That's again the same flow rate. So we can change this to 300, let's say, and see what's happening. What is happening now is the first pump has to run at 70% speed and the second pump needs to run at 57. So assume we did the reverse. So the first one at 57 and the second one should run at 70% speed. So that's clearly show us that if you have a different lengths or resistance in the pipeline between the pumps, and we have the pumps here are identical, we cannot run them at the same speed. So let's see what we can do about it. We can see here at about 4 kilometer. You can see it's 80. It's 80 because it's divided equally. But if you have this is 3 kilometer, then this one should run at 70% speed. And because we need only 51 meter. The second one, we need 68 meters. And that's why we need to run it at 80% speed. Now we'll see a different scenario where we run both pumps at same speed, and we run them to the maximum. So we'll see what's happening here. If we have a 2 kilometer and 2 kilometer, so the maximum flow rate in this case is 520 meter cube per hour. Both pumps are running at 100%. So if we run this through 3 kilometer, we can see now that the total flow rate is 467, is less, and the resistance for the second pump is minus 20. So how we did this calculation is we based that suction is 0, discharge is 0, regardless of the regardless of the suction pressure of the second pump. We use them as if it is a close coupling, but we move this guy in the 3 kilometer mark, and we found what would be the pressure here. So this guy will deliver 103, and this guy will deliver 103. But because we need 123 to pass the fluid from the discharge to the suction, we need 123, but this guy can only deliver 103. That means we are short by minus 20. Now we need 80 in this section, but we already had lost 20, which is matching the 103, which is the maximum this pump can give us at that time. So it's clear, very clear, that we cannot run both pumps at 100%, and we expect, or the same speed, and we expect them to deliver the same flow rate with the same head, while we have a different resistance in front of each one of those pumps. So as we established before, if we have two pumps close coupling and then we have LIC, the LIC will run both pumps at the same speed, and we are satisfied with this as acceptable control scheme. If we moved the one pump to the middle of the line, then we have the same scenario. We expect that to do the same scenario, but in fact we have another issue we have to consider. Now if you look at the second pump, and because it's far away from the first pump, we could run into the possibility to have the suction pressure goes below the minimum suction pressure, and this pump will be cavitating. So to reduce the likelihood and the risk of cavitation in the pump, we introduce a new PID loop, which is a PIC in this case, which monitors the suction pressure and reduces the speed of the pump to maintain a minimum suction pressure at the pump suction. So in the same scenario, we have the LIC sending let's say 70% speed to the second pump, and then the PIC monitored the suction pressure and found that the suction pressure is so low, so now it has a lower, let's say 60% speed, and their selection here will use the lowest speed, which is 60. So this pump will be running at 70, this pump will be running at 60. So you think that in this case we have acceptable working scenario, while the LIC will try to push as fluid as much to maintain the level, and this PIC will run this pump to avoid any cavitation in the suction of this pump. However, in a lot of cases, this scenario is not working in let's say smooth as it intended. So this is the control scheme which we use in this scenario, but to make it smoother running, and I found that a lot of the operator, what they do is they decouple the LIC and the PIC. So in this case, this pump will run to satisfy the level, and this pump will run to satisfy the minimum suction pressure. In this case, regardless of what's this pump running at what speed, so if this pump running at a higher speed and you have a higher pressure here, so this pump will be running at a higher speed to reduce the suction pressure to a specific value, which around the minimum suction pressure. So now we can share the load between the two pumps without sharing the LIC signal for both of them. So again, what we do is running the first pump on an LIC and run the second one on the PIC, which is suction pressure. If this pump runs at a lower speed, that means this pump now need to reduce its capacity. The suction pressure will go down, the pump will go lower speed as well. So this is how the system worked in much more smoother than the previous scenario, which we have the LIC drive both of them at the same speed. Thank you, and see you in the next video.